Hi class, welcome to chapter 13.7. Today we're going to talk about strategies for determining convergence. This is very similar to what we did earlier. We're talking about strategies for trying to integrate. Um, Certain methods of integration work better for different integrands, right? Same thing for series. Different methods for testing convergence work better for different type of series. And so this is really just a review of the different series that we've gone over and the different types of tests, and when to apply which when, and then a few examples. Okay, so let's go and get started. So in this section, we're going to cover what to be looking for when we're looking for convergence. The form of the series helps us determine the best guess approach for which methods we want to attempt. So the first thing that we should probably look at is is it easy to see that the limit as n gets large does not go to zero, right? So if my sequence does not decrease towards zero, then it's probably divergent. Okay, so if the limit of the sequence of terms as n goes to infinity does not go to zero, then the test for divergence is a good option because that's literally what the test of divergence is, right? If it's a p series, we can tell pretty quickly by looking at it whether or not it converges or not. So if our sequence has the form 1 over n to the p, if p is larger than 1, it's a convergent p series. Um, if it's equal to 1 or less, then it's divergent, right? Is it a geometric series, right? So does our integrand, or I'm sorry, does our sequence terms have the form of r to the n minus 1 powered or some form of that? If the absolute value of r, right, this base is less than 1, then we're convergent. Um, if it's equal to 1 or larger, then it is divergent, right? Do our terms alternate in sign, plus minus, plus minus, plus minus? If they do, then the alternating series test is a good test to use, okay? Is it similar in form to a p-series or a geometric series? Two important series that we know about. If it is, then we should probably compare it to a p-series or a geometric series, okay? Is it similar in form to a p-series or a geometric series and all terms are not positive? Then we can use the comparison test on the absolute value of the sequence to test for absolute convergence. So that's pretty nice as well. If the sequences are equal to f of n, meaning that if I plug in the integer n into a function, I get the same output as the term in my sequence, then and it's positive and decreasing, then I can use the integral test, right? I can integrate from 1 to infinity of that function, and that'll tell me whether or not I diverge or converge, right? So I use the integral test. If I have factorials or products of n, including constant raised to powers of n, then I would want to use the ratio test. Okay. The ratio test should not be used for p-series type of questions or algebraic functions, polynomials, rationals, and root forms. It can be used, but you're more likely to end up with something that's inconclusive. Okay, so your results may return inconclusive. So when you see factorials, factorials are this is kind of the only test that we do have to talk about the convergence. So that's a good giveaway for when to use that test, right? If I can write the general term of my sequence in the form of something to the power of n, then I should use the root test because then I'm taking the nth root, and then it'll tell me whether I'm absolutely convergent or divergent or inconclusive. But generally, that's a good indicator. Okay. So we went very, very briefly over, some of these conditions. So let's review and look at each of the different tests that we have, right? So our test for divergence, if the limit of the general term as n goes to infinity does not exist or does not go to zero, then our series is divergent, right? That's the first thing that we talked about was the test for divergence. The integral test says that if we have a function that is continuous, positive, and decreasing on 1 to infinity, and the integer values match up with the sequence terms and the function values, then my series is convergent if and only if the improper integral from 1 to infinity, okay, over the same um, interval is convergent. Or, in other words of saying that, if my integral that matches that of that function that matches the function with the sequence, that is continuous, positive, and decreasing, is convergent, then the series is convergent. If that integral is divergent, then the series is divergent. The comparison test says that, say we have two series, one that I'm given and then one that I'm using to compare against the one that I'm given that has all positive terms. If my second series, the one that I'm coming up with, is convergent and it is larger in value everywhere than the given series, then the given series is also convergent, right? So if I have a series that is dominated by a convergent series, that series has to be convergent as well. If the series I come up with is divergent and it is smaller in value, it is dominated by my given series, then the series that I'm given has to diverge as well, right? If my terms are always bigger than another series that's divergent, it has to diverge also. The limit comparison test was a way for us to kind of double check this work, right? So I have these two series. Again, they have positive terms. If I take the limit where I'm taking the ratio of those, right? My given series divided by um, the one I'm comparing it to, and I look at what happens when it goes to infinity. If that equals a constant number, right? A finite number that is positive and non-zero, then my given series does whatever the one that I chose to compare it to does, right? So if the one that I chose to compare it to diverges, and so does the given series. If the one that I'm comparing it to converges, then so does my given series. The alternating series test, so if I have a series that alternates in value, plus minus, plus minus, plus minus, okay, and every new value in the series is smaller in value than the previous, and the limit of the general term goes to zero as n goes to infinity, then the series is convergent. The ratio test is that if I take the limit as n goes to infinity of the ratio of me looking at my general sequence term plus 1 divided by my general sequence term, right? If that limit is less than 1, then that series converges absolutely. If that limit is larger than 1, then that series is divergent. And if the limit is equal to 1, then I have an inconclusive test, meaning that no conclusion can be made based on this test, and I would have to then, go apply one of these other tests, right? Something that maybe is more appropriate, which we can determine by looking at this list of 8 sort of guidelines, sorry, 9 guidelines. Okay. The ratio test, so we just went over that. The root test is very similar, except I'm taking the nth root of the absolute value of my general term of the sequence. Again, if it's less than 1, then my series converges. Absolutely. If my value is larger than 1 for that limit, then the series diverges. And if it is equal to 1, then it is an inconclusive test. Okay. So let's do some examples. So here we have n to the fourth over 4n for the general term. This n term here makes it very clear that we should probably use the root test. Although we saw previously that I was able to do the ratio test and this worked very well. So we can really apply either one. Okay, so here we're going to use the ratio test, although the root test would be more than appropriate. And I would get, if I did the root test, I would have n to the 4 over n over 4 as n goes to infinity. And we saw already that 4 over n would go to 0 faster than n goes to infinity. So this numerator would go to 1, and I would end up with 1/4. Okay, so just looking at this by inspection, I know what the limit's going to be by doing the root test in my head. And if it goes to 1/4, there we go, 1/4 is less than 1. So that means that this will be absolutely convergent. Okay. However, we're going to do the ratio test. So our answers definitely should match up. So I take the reciprocal of this, and that's on the right side. I have n plus 1 everywhere, and that's on the left side. Okay. So what's going to happen here is that this 4n and this 4n plus 1 are going to cancel, and I'm left with just a 4 on the bottom. Here I'm going to have n plus 1 over 4 over n to the fourth. Okay. The initial term, or I'm sorry, the highest power here, the degree of the polynomial on top is n to the fourth. This is n to the fourth, so my limit is just the leading coefficient, which would be, 1 and then 4 here. So I get the exact same value for my ratio test as I would for the root test. This is less than 1, okay, which means that this converges absolutely, right? So maybe you do the root test on this just for some practice. I know I walked you through it, but maybe you just do a quick scribble on your paper and you know, see that you can work this out on your own as well. So here I have 1 over n cubed plus 1 over 3 to the n. So here, if I were to do something like the ratio test, that I could do it, but I'm gonna have to, it'll be a little bit funky. Um, it's completely doable though. The root test wouldn't work so much because these are being added. So if I did the nth root, I'm not actually going to get rid of this root. Um, Maybe what would be easy here, because I have two sums that are being added together, I could split this into one series plus a whole nother series, and I can do a comparison of I can do a p test, or I'm sorry, a p series on one, and I can do the nth root, um, the root test on the other. That would be okay. If I look at this as a whole, I could probably do some sort of a comparison test, right? But it would be much easier to split these into two different parts and look at this as the p series and this as using the ratio test, right? So 1 over n3 is the p series with p equals 3, which is larger than 1. Okay. And this is the geometric series, right? So I could use the ratio test, but I didn't notice that it was a geometric series. Much easier to talk about it in that term, in those terms, right? So 1 over 3 is less than 1, so this is convergent as well. So this is the sum of two separate convergent series. So it's much easier to split these apart. Okay. Here I have n sine 1 over n. The ratio test wouldn't necessarily be super good here because sine of 1 over n wouldn't cancel with a sine 1 over n plus 1, for instance. So a ratio test wouldn't really be helpful here. It's probably going to come up inconclusive. Same with the root test because there's no roots here at all. Probably a comparison here, right? Because I have sine. I know sine does not get larger than 1 in value and does not get smaller than -1 in value. So this is it's possible that this alternates in sign as well. I'm sure it does. So maybe we could look at, I'm just guessing here, a comparison here, right? Or an integral test as well, especially since it's a function of sine. Okay. That's probably the better one because here it alternates in yeah, in sign, so it might be a little bit work to just look directly at the limit. So let's see what we go ahead and go with for the second and third example. So here I'm going to take the limit of n times sine 1 over n. Okay, I can split this part to 1 over n over 1 over n. Okay, using L'Hopital's rule, I differentiate the numerator, differentiate the bottom. So what we're doing, if you're not clear, we're using the test for divergence. We're basically just looking at the limit here and seeing what it does. Okay, because I'm not too sure what it does by inspection because it's a sine. Sine alternates in value. So is it decreasing in value as we go or is it not, right? And so let's see. So we'll do some fancy stuff. We could split this apart in this way, do L'Hopital rule. Okay, here we see that this primary term will cancel out and I'll be left with the limit as n goes to infinity of cosine 1 over n, okay, which is going to be 1, okay, approach 1, which is not 0, which means that this is divergent, right? It does not pass the divergence test Remember, the divergence test will only tell you whether it diverges or not, right? It does not tell you whether it is convergent, right? So either it diverges or we can't tell if it diverges. It cannot tell you whether or not it converges, right? So here I get a value that's non-zero, so I know that it diverges by the test for divergence. Okay. Here I have a factorial with the power of n to the 4n. Both of these have a power in n. Very clear here. I should probably use the root test, although I could probably use the ratio test as well. So we'll do the root test. That'll get rid of all of these n's, and I'll be left with n factorial over n to the fourth. If I look at this limit, which one do I think grows faster? Does factorial grow faster than n to the fourth? Um, I don't know. So let's expand this, right? What does the factorial look like? N times n minus 1 times n minus 2 times n minus 3, and then n minus 4, and then I continue going, which is why I have this factorial here. I don't have to continue because I have n to the fourth, so that's just n, 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 n. Well, this is 1, okay? This here is less than 1, less than 1, less than 1, but this portion of it is just going to continue to increase more and more and more, right? I'm multiplying by whole numbers continually. So this is gonna just um, this is gonna continue to grow. Okay. So here what I'm doing is I'm just separating everything, right? So the n over n is 1. Here for this term, n over n gives me the 1 and minus 1 over n. So this n minus 1 over n, I'm just applying this denominator to both terms separately. Same thing here, 1 minus 2 over n. Here, 1 minus 3 over n. Okay. When I look at what happens as n goes to infinity, this goes to 0, this goes to 0, this goes to 0. So I'm left with just 1 times 1 times 1. And this n minus 4 here just continues to get larger, like I said. So by inspection here, I kind of said the same thing here. I'm just kind of mathematically showing you. So that goes to infinity. So like, we saw by the ratio test, if this is larger than 1, right, then it diverges. Okay, so it is divergent. Here I have 1 over n to the 1 plus 1 over n. I know this may be confusing to you notation-wise for some people, but this is not 1 plus 1 divided by n, right? It's 1 plus 1 divided by n. So this is not 2 over n, so, you know, the parentheses would be here with 1 over n, so please don't confuse that and make an unnecessary mistake. Here, this is kind of looking like a P series-ish. Not really. I probably want to like do some comparisons here, right? I do know that I have 1 plus something, so it looks like a P series with P larger than 1, except that this will go to 0, right? So is it really like a P series? I don't know. Let's do some math, right? So the way that powers work, right? I have the same base and I'm adding 1 plus 1 in. So I'll just go ahead and separate that in this way. Okay. Um, here I am going to do a test for divergence. I'm just going to take the limit of this and see what happens. And so I can rewrite it in this form. Oh, I'm sorry. No, I am not doing test for divergence. I am doing a comparison test, a limit comparison test. I'm going to compare this with the harmonic series, which I know diverges, and which is nice because that allows me to kind of cross this out. So I'm doing this kind of trickly in a way that I know I'm comparing this to a series that I know what happens to it, the harmonic series, right? I know it diverges. So the nice thing is that now that I compare this, right, I have my series on top. On bottom is the series that I'm trying to compare it to. So if we come back into the rule, okay, my series over the series I'm trying to compare it to, all I need is that it comes out to a positive finite value, that it's not infinity and that it's not negative. And then if that's true, the top will do whatever the bottom does. Okay. So past that already. Okay. Obviously, these two things are going to cancel, and we're going to have just 1 over n to the 1 over n, which is equal to 1. Again, this power is going to go to 0 faster than n grows. Okay, so you can use L'Hopital's rule to check that if you need to, um, right, as far as limit goes. But we've seen this, like, this is like the fourth time already. So we know that this goes to 0 rather quickly, right? This is going to go 1, 2, this is going to go 1, 1/2. So the power is going to drop a little bit faster than this is going to grow. So that means that this is going to go to 1, right, and to the 0 power. So this is going to go to 1. So the limit of this thing is 1, which is a finite positive value. And so since the denominator function, right, series, the harmonic series diverges, the numerator series diverges also, right? So divergent by the limit comparison test. Okay. I think this is our last example. So here we have 2 to the 1 over n minus 1 over 1 over n. So we actually did one very similar to this a while back. I think the easiest thing to do here would be some sort of a comparison test. Okay, so it looks like we're just going to take the limit of this instead, right? We're just going to check to see right away if it diverges or not, because if we could tell it diverges, then we don't have to do anything. If the limit or the limit test for the test for divergence is inconclusive, right? It does go to 0, then we'll have to apply some other sort of test. Okay. So here, looking at this, I know that the denominator, this is going to go to 0. Okay. But it's written in a weird way, so I probably want to flip that around. Um, looks like we're going to use L'Hopital's rule instead. Okay, which is nice. So again, this numerator has a term that cancels with the denominator, so that'll be nice. So I'm just looking at what happens with 2, 1 over the n, natural log of 2. Here, we know that this is going to go to 0, so this whole thing is just going to go to 1. So this limit is natural log of 2, okay, which is a positive value, which means that it does not go to 0. And so by the test for divergence, it fails. There you go. Okay, therefore diverges by test for divergence. Okay. So that's sort of the way that we look at these problems when we just have a series in general. Try to apply the best test um, that we can. Root test and ratio test are always great options. Sometimes you can just take the limit and see that it doesn't go to 0, and then the test for divergence is super helpful as well. Okay, so we'll see you guys on the next section. We're going to start talking about power series. So the last sections of this chapter are all about power series and how to deal with that. So basically what we're doing is we're going to be approximating functions by using series, right? So see you guys on the next section.